Talking about the standard deviation, the first thing that we need to talk about are these deviations about the mean. We simply want to know the difference of every observation minus the sample mean. These deviations are going to help us see how each observation is spread out. And then the standard deviation is actually going to give us the average of those deviations. So how do we get that value? Well, the first thing is we would want to get the ith deviation for each value in the sample. And so we looked at, we can look at example 3.8, looking at these zucchini weights to see how we would create those deviations. We have 5 weights given in ounces, and the first thing to find these deviations is to first find the sample mean. So our sample mean, we will add each observation. And since it's just 5 values, I probably will just do this one by hand instead of going into jump or something else. So we add up our numerator, we get 32.5, and we divide that by 5. So here our mean is 6.5. To do these deviations, I will often create this chart where I have my xi values, and those are just each of the observations. And then where I've taken those observations and subtracted the mean. So here's 6.2 minus 6.5, we get a negative 0.3. 4.5 minus 6.5, that gives us a negative 2.0. 6.6 minus 6.5 gives us a 0.1. 7.0 minus 6.5 gives us a 0.5. And then 8.2 minus 6.5 gives us a 1.7. And so these are all of your deviations from the mean. And one thing that's really interesting here is when you add these, it will actually always equal 0. The mean is a balancing point. It's where you have balanced the weights of your values in your sample. And so, or sorry, I shouldn't have said balancing weight. It's a balancing point. There we go. So it's a balancing point, and if the mean is your balancing point, then the differences from all the values to the mean will balance out, and that sum will always be 0. So that's just an interesting observation here, is that the sum of these deviations will always be 0 for any data set. Take this a step further to talk about what's called the sample variance. And here, this is where you add all of the squared deviations about the mean and then divide that by n minus 1. Now, the reason we divide by n minus 1 has to do with the fact that we only have n minus 1 degrees of freedom. So think about this. If you knew the mean, so if you knew the mean was 5 and there were 5 values and you knew what 4 of those values added to, then there's only one value left that it has to be. So you kind of lose a degree of freedom once you know the sample mean. The last value is forced. So, I know that's kind of a weird thing to think about, but, just this n minus 1 that we're dividing is by the fact that we're using the sample mean here in this formula, and you only need n minus 1 values to know all of them. So it's just a formula, and we won't actually use it most of the time. So to do the variance, you're going to square all of those deviations, add them up, and divide by n minus 1. To get the standard deviation, you simply take the square root of your variance. So let's go back to the zucchini data and get the sample variance and the sample standard deviation. Now I'm going to make a column for all of these xi minus x bar squared. So we'll square negative 0.3. And whenever you square a negative, you always are going to get a positive. So really, you can leave off the negatives here when you're squaring, because you do have to put them in parentheses. You do want everything to be positive. By getting the positive values here, which I forgot to write all of the squares. Make sure all of those are squared. But by getting these squared values, everything is going to be positive, and then we'll no longer have that issue of us getting a sum of 0. They're all positive, you always will get either 0 or a positive value. So I'm just squaring all of these deviations. .7 squared. From here, we can add all of these squared deviations. So we'll add 0.09 plus 4 plus 0.01 plus 0.25 plus 2.89, and our sum here is 7.24. To get the variance, so to get our s squared, you take that sum and divide by n minus 1, which in this case, n, the sample size is 5. So our variance will be 7.24 divided by 4, which is 1.81. And then to get the standard deviation, which is usually what we're interested in, it's that average spread from the mean, you do take the square root of that value. And the square root of 1.81 is 1.345. So there's our standard deviation S. Our sample variance is 1.81. But as you can see, this is a rather intensive process for finding the standard deviation. And so sometimes when we're doing these calculations by hand, there's an easier way to do this. So we want to be sure that we can do these calculations without technology. If we had technology, this is going to show up and jump in those summary statistics. It's easy to get in technology. But if we're doing this by hand, this formula is time consuming. So there's an easier computational formula for standard deviation. It may look a little more complicated, but it really is much simpler. So here, if you knew the sum of the x squareds, so you take each x, each observation, and you square it, and add all of those up, and then you subtract, you subtract 1 over the sample size of the sum of the x's squared. That gives you this part. You divide that by n minus 1, and that will give you the variance. Now, you may say this still looks kind of complicated, but notice here that we never had to find the sample mean. And so that's one less step, and here all we're doing is either adding the squared x's or adding the x's and putting it into the formula. So let me show you how you can get the sample variance and the sample standard deviation when you know the x squareds and the x's. We're going to use our zucchini weights, and we can go ahead and get the sum of all of the x's just by simply adding these together. And in your homework, you'll actually already just have the sum. You won't even have to do this part of the calculation. But if I just add all of the x's, I get 32.5, and then we'll square everything. So 6.2 squared is 38.44. 4.5 squared is 20.25. 6.6 squared is 43.56. 7.0 squared is 49. And 8.2 squared is 67.24. And then we just add up these squared values, just adding everything in this column. And that gives me 218.49. Now to see how this goes into the formula, we're looking at 1 over n minus 1 times the sum of the xi's squared minus 1 over n, the sum of the xi's squared. So we'll put this into our formula. It's 1 over 4. The sum of the xi squared, that's this number, the 218.49. And then we do 1 over 5 times, and then the sum of the i's squared, you would do 32.5 squared. So I know this is still a little bit of computation, but it is a little less work than the other one. So using order of operations, I will go ahead and do my exponents here. So 32.5 squared is 1056.25. And then we'll do our multiplication here. Multiply that by 1/5. So we have 1/4, then 218.49 minus, that's 211.25. Then we can work inside my parentheses. So 218.49 minus 211.25, that's 7.24. And now we see where we ended up getting to the same final step to get 1.81. So here, my sample variance is 1.81, which means the standard deviation is the square root of that, which is 1.345. So that's how you use the computational formula. And like I said, in the homework, you will be given these two values, and you can see where I put them into the formula and then simplified. A few last remarks about the variance and the standard deviation is we do have a population variance, and that is going to have this Greek letter sigma squared. That little, it looks kind of like a O with a little line. So the population variance, the variability for the entire population, will be sigma squared, and the population standard deviation would be sigma. Now again, we don't always know the entire population, so these are typically things that we have to estimate. Now, knowing S squared alone really doesn't tell us a lot about variability. It can be helpful to make comparisons between groups, but knowing the variance it's not always that helpful. But the sample standard deviation S is used in a lot of the statistical inference procedures that we'll be doing in this course. Your units for your sample standard deviation will always be the same as those for the original data. So with our zucchinis, we were in ounces, and so the mean, the median, and the sample standard deviation all have the unit of ounces. It is possible for your standard deviation to be 0, but that means that there's absolutely no variability in the data set. So all of the values are exactly the same. There's no difference. But it's impossible for your standard deviation to be negative, because think about how we calculated this. We squared a lot of values. And so in that process of squaring, everything became positive. So it's not possible to talk about a negative standard deviation. And now we will go where we have multiple samples. And so if you ever see this notation S with a little x squared, that means that you're looking for the sample variance for the X observations. So sometimes subscripts are in there to help us look at, whether it was the list of X's or the list of Y's.